Hey Sloan, how you doing? It is Monday. I had a great weekend. Got to play some Resident Evil 4. Really good game right there. Logging in, trying to beat on professional mode, S plus ranking. It is hard. Video games are tough. But got to relax a little bit. My contacts are still going crazy. A little less crazy than usual. Had anniversary weekend. Getting the assignment open as we talk about this. We've got some chapter 16 talking about null hypothesis, type 1, type 2 error, stuff like that. So let's get the chapter 16 quiz up and going right here. And here we go. Well, poll asked, in a poll, the president, yay, nice, thank you, Sloan, right there, 100 points. Me Botswick in the chat. In a poll, the president's approval rating stood at. Okay, let's find out that one. In a poll, the president's approval rating. In a poll, the I don't know why my right contact always going a little crazy. Okay, really good question right here. In a poll, the president's approval rating. Let's go copy paste it and put it in the notes. Here we go. We got 2 out of 3, stat 201, chapter 16 quiz in a poll. Okay, let's go check it out. The only thing is part B where you get the question. Yeah, let's take a look at it. Okay, so you made the 90% confidence roll right away. If you did, that's awesome, Sloan, right there. Because they give us summary statistics here to start, and a lot of people get confused on what do I have and what do I need. So when we look at this graphic right here, let's go ahead and grab the information. Get a Word document up and going. Hey, good to see you. Here's Cassidy, I think I saw in the chat. Kelsey, good to see you here, Kelsey. Ask any questions you got, Kelsey. We're going to drop the first question in, but drop those questions you got, and we'll start looking at them. Okay, so Sloan, 2 bits of notation. What are they? Let's get the notation perfect right here. You're welcome. We'll get this done really quickly, I think. Yeah. So what are the 2 things in the notation right here, and then we need to get another thing from that. So notation, we need to be good at it and quick at it. And then we are going to get the notation, and then we're going to solve the confidence interval pretty quickly right here. So what is the notation that I've got circled? We need 3 things. 2 of them would be good. 3 of them would be great. What is the notation right there? Making sure that we know the exact notation because this is in a poll. So we have to think about what this is right there if it's from a poll. So what is the notation for this? We'll get that 90% confidence interval pretty quickly. And they're asking, do you approve of the president? Great job, Sloan. 100 points right there. Yep. Piat and Q are compliments of each other. This is a question of, do you approve of someone? So it's a yes, no question. So it's categorical data, random, 10%, and success failure conditions apply. Z-score is going to be equal to 1.645. That's the Z-score for a 90% confidence roll. I've got the link in there. Great job. Sloan's already on fire with these answers today. I've already got the link here for it. Now, it does say that, but go to between, go to 90%, and then round usually to 3 digits, 1.645. Make sure you're on the normal curve right there. So if you're looking for the Z-score for a 90% confidence roll, you need to go to the normal curve. You need then probably to round to 3 digits, I would say. Sometimes 4 doesn't hurt. Then make sure you have 0, 1 for Z-scores. That's the standard normal curve. Put in 90%, put in between. Just make sure your screen looks like my screen right here with normal selected, 3 digits, and find X using a p-value, which is an area right there. So now that we have the Z-score, we have all the components needed. Exactly. Always safe to add in those extra decimals just in case. Contact me or your instructor if you feel like you didn't get the answer right. But a lot of times when it comes to the T, if this is the T, a lot of times people use the Z instead of the T. Now this is Z because this is not a interval for the mean. So we don't have degrees of freedom. It's just a Z-score. And the last part of this is P hat times Q hat over N square root. Now we plug in the numbers. We're just solving the first part of this problem right here to figure out a 90% confidence interval for the approval rating. We plug in 1.645. We square root 0.53 times 0.47 over 1200. This last portion is the standard error of the interval. So we're going to solve that first, which is going to be, got the little help rectangle over there. 0.53, 0.47, 1200. There it is right there. We square root. I'm so not used to this calculator yet. There it is. That's square rooted. There it is. That's the square root of it right there. 0.0144. I think that's correct. That does look correct. Times by 1.645. There's the value right there. Now we're going to take 0.024. So very important to know, 2 letters, Sloan. What is this last portion right over there? Just type 2 letters in the chat to confirm you know what that is, because we should know everything after the plus or minus is this right here. So we should know that we're solving this. Oh, great job, Sloan, right there. I think Sloan's already got the answers perfectly right there. And Sloan's already another 100 points. Yep. And so what are we? Sloan has added and subtracted the margin of error. So Sloan knows what to do right there with those numbers. And then you create the lower and the upper of the interval, which I'm just going to copy Sloan's answers right there. And this can also be done with one prop z int on the calculator. So there are ways of doing it with the calculator shorthands. So now we put in the answers right here, round to 3 digits. There we go. Based on the confidence roll, do you think it's the same as 48%? And so here's the thing. When you look at a confidence roll and you interpret it, I am 90% confident that the president's approval is contained in the true president's approval rating is contained in the interval 50.6 to 55.4. So would you reject or not reject 48%? Would you reject or not reject 48%? And then think about why. Because you're saying you believe it's somewhere between 50.6 to 55.4. You're 90% confident that the approval rating, if you were to talk to all people, so it's not the poll's approval rating, because you know what that is. You know what the sample was. So do you think the truth is 48%? Do you have evidence for or against that, and why? So think about what you're saying. I am 90% confident the president's true approval rating is somewhere between 50.6 to 55.4. Yeah, exactly. Yep. I would reject that because 48 is not in the confidence roll. Oops. No. Please tell me we didn't lose our work on that. Check answer, 100%. Yep, that's it, Sloan. So this points to how you can use confidence intervals to do hypothesis tests. So it's the same thing as doing a two-tailed test to say it's the same as or not the same as. Notice that they do the same, which would be the alternative. It's not the same, which would be the does not equals alternative. So you could use this 90% confidence interval to reject at the 10% alpha level, 48%, or you could say it's greater than with a 0.05 alpha level. So this is pointing to confidence intervals and tests come to the same conclusion. Yep. And that's the key concept to learn, is that like you can use a confidence interval to run a test by looking to see if values are inside the confidence interval. If that value is outside the confidence interval, you can reject it at the point at 1 minus confidence interval, 1 minus confidence interval level. And it looks like this. Since we ran our test, and we'll do the next question here. Since we ran our test with 90%, or our confidence interval with 90%, what is the associated alpha level that a two-tailed test would come to the same conclusion on? What is the associated alpha level that a two-tailed test would come to the same conclusion on? So remember, it's a two-tailed test directly relates to a confidence interval, and a 90% confidence interval would come to the same conclusion as a what-tailed test with, well, two-tailed test with what alpha level. So you can look at the drawing to get a hint of how it works mathematically. So it's how a confidence interval comes to the same conclusion as a two-tailed test, since we did with 1 minus confidence level of alpha. Close. It wouldn't be 0.01. It'd be 0.10, because this is like 90% of the area. So these are complements of each other. Yep. Great job right there. Yeah, it's just, it works like that. And don't worry, I was making so many errors on Thursday. Let's do the next question right here. We're just going to rock and roll through these questions. But which of the following is true? Which of the following is true? Good work, Sloan. This is a fun one. Errors. We can do errors really easily. Is it this one? No, it's a different one. A lot of good questions, just some basic knowledge here. Here we go. Is it this one? No, wait. A lot of which of the following is true. the null hypothesis is true, you'll get a high p. Oh, here we go. Okay. Ooh, this one's weird. Alpha levels independent? Yeah, Jackson will do it next. You got it. Here we'll do a bunch of which of the following is true. So let's do a bunch of these, Sloan. And we'll just let people find, because this is a bunch of good basic knowledge. Okay. Yeah. So here we go. So you don't want to read their answers. You just want to think through it for yourself because you want to make sure you have the knowledge. If the null is true, you'll get a high p-value. That's kind of true, but it doesn't mean you will always get a high p-value. If the null is true, you're likely to get a high p-value because let's say Brian can run a 6-minute mile. Then you would expect to see Brian run a 6-minute mile. Now, random variation could have you end up on the far side of the curve and make an error, and you could think Brian's faster or slower. But the most likely results are around the null. So I'm a little worried. Let me look at the false statements right here. False. The p-value is dependent on the data, not the hypothesis. Yeah, exactly. Boom. Exactly what we were saying. The p-value is dependent on the data. So you could see Brian run something really fast or really slow, and the data is going to have you reject or fail to reject the null. It's likely you'll see if Brian is a 6-minute mile runner, if it's true Brian runs 6-minute miles, then it's likely to see something in here, but you're not guaranteed to see something here. You could make errors. So that is the perfect answer. If that's not the answer, I'm going to be shocked. If the p-value is true, a p-value of 0.01 will occur about 1% of the time. So that's called your what error rate? Well, if you set it to this, that is exactly what a p-value means. The p-value is the probability of our results or results more extreme happening by random chance given the null is true. So if the null is true, results that would occur 1% of the time would occur 1% of the time. It's almost tautological. Well, no, that's not a margin of error right there. That is just saying that these results, like if the null is true, then you would see Brian run something down here. Like if this is the bottom 1% of the curve, you would see Brian run something down here 1% of the time due to random chance. Did they add the random chance on there? Let me see. Did they say that? I wish they did. They should say would occur 1% of the time due to random chance. Be better. This is actually true right here. Let me read the false statements just to double check. False, if the null hypothesis is true, then a p-value, no, would occur 99% of the time. If the null hypothesis is true, then a small p-values are extremely unlikely. Well, I mean, that is unlikely. If the null is true, then a p-value will occur less than? No. See, the learning objective on this really isn't great because a p-value is the probability of our results or a result more extreme occurring by random chance variation given the null is true. So if Brian is a 6-minute mile runner, then he will run a mile this fast or faster 1% of the time. Isn't the error rate just like the likeness? Yeah. Mm-hmm. So if you set your alpha to this, so you could run a less than test to see if Brian's faster than a 6-minute mile with an alpha equal to 0.01, and you would only make the error 1% of the time where you would reject the null. So that's you setting your error rate. So it's possible that you could think I'm faster than 6 minutes, but I just had a really great mile. Does that make sense right there, Jackson? So Jackson, another 100 points. Great answers right there. It's possible, and this is the error rate. The alpha is your type 1 error rate, and beta, which is not 1 minus alpha, is type 2 error rate. So you are correct. So the alpha is the willingness to say this percent of the time we'd see something as extreme like that makes us think we can reject the null, even if the null is true. So with a 1% alpha, you will reject the null where 1% of the results that would happen if the null is true would occur. So make errors. Yeah, it can really trick you. Watch me get tricked by one. I'm not impervious to their tricks. I try to be, but sometimes they don't word it perfectly. P-value of 0.90 means the null hypothesis has a good chance of being true. Well, remember, the p-value is the probability of our results or results from our stream happening by random chance given the null is true. It means we saw something that was likely to occur given the null is true. So if the null is true, this result or result more extreme than it would occur 90% of the time. To go back to the running graphic again right here, you would have had to have landed If you got a p-value of 90%, Brian's a 6-minute mile runner, you landed somewhere in here, and a result as extreme or more extreme on either side would occur about 90% of the time. So the result we saw was very likely given the null is true. It doesn't mean it's likely the null is true. So I think they're getting at that right here with missing, and this is a decent way, but they're trying to point to people think it means the null is true. No, it means what we saw. Oh, they should expand. If that's the answer, they should have expanded. Whether a p-value provides evidence for the null, no. The p-value means that the null hypothesis, no. The p-value says nothing about the probability that the null hypothesis is true. So what the p-value says, and that should be the answer, is that what we saw was likely given the null is true. Our results, the p-value is the probability of our results or a result more extreme given the null is true. And so that looks right there. A p-value of 0.90 is strong evidence that the null hypothesis is true. Yeah, not my favorite sort of questions on this. Like, they're really just hammering down one point on what is a p-value. Okay, let's see what this says. The p-value provides strong evidence that no. The p-value provides this p-value solely provides no evidence that it's false. What? This p-value solely provides no evidence that it's false. Well, that's just, if that's the answer, I'm just gonna blow up. Whether a p-value provides evidence for the null depends on the alpha level. Well, we don't provide evidence for the null. I really don't like their wording right here. Yeah, I think this is okay, good. This is actually it. And this I'm just the way they've worded this. I understand what they're getting at. When we provide evidence, we only provide evidence for what. I've said this a lot in class. We only give evidence for the what. We only give evidence for the what. The answer is going to be C. Because we only give evidence for the what. Well, not for the truth. We have the null and we have the what else. And then I say this is the evidence-based claim. And it's the way we do the wording too. If you think about the wording we have when we say, I reject the null, I have evidence for the what, for the alternative. So the way they say this here is insane. The p-value solely provides no evidence that it's false. They should say the p-value is not used for evidence the null is true. The p-value is used for evidence to reject the null, i.e. say it's false, and say we have evidence for the alternative. So they should have maybe even said the p-value is solely used to provide evidence for the alternative. That would have been better, right? Stated right there. Whoever wrote this wrote a really weird way of saying it, but you could have just said the p-value is used for evidence for the alternative, i.e. our results were unlikely given the null is true, evidence for the alternative. Unless I've misread something here. Really, I did. It's not this one. Yep, that one's good. Was this one true? No way. Where did I misclick something? Okay, so it's this one. B. If the null hypothesis is true, a p-value will occur about 1% of the time. What? If the null hypothesis is true, then a p-value of 0.01 will occur. Wait. False. Wait. If the null hypothesis is true, a p-value of 0.01 will occur about 1% of the time. False. If the null hypothesis is true, then a p-value of 0.01 will, or less, I think that's the answer. Let me read over this. If the null hypothesis is true, then a p-value of 0.01 or less. Oh my gosh. They're literally getting into the probability of our results or results more extreme part of it. That's... So what they're pointing out here... Wow, that's so particular. So particular. Sorry. This question... I feel like people are going to learn so little from this because they're literally just going over the definition of a p-value. They're saying if you have a result right here. So here's the result. And this result has a p-value of 0.01, which is the probability of the result or the result less than. So the way they word it first is that this right here has a 1% probability. but the p-value is the probability of the result or the result more extreme. So this is wrong right here. It's that the 1% is the probability of our result or result more extreme. Hey, Rachel, good to see you here. My Pearson got me on one of the wordings because they're being very particular that it's not that the result at a p-value of 0.01 has a 1% probability. It's that the result a p-value of 0.01 or less. It should say the result, the observation. Yeah, I really don't like that they're saying the p-value of 0.01 will occur. Results that occur with a p-value of 0.01 will occur 1% of the time, or like down here, it's talking about this. So the improper interpretation which they give is this right here on this line, which that's where it is not 1% of the curve, but the proper interpretation of 1% or less of the time is to the left. So, wow, that once again, the p-value is the probability of our results or a result more extreme happening by random chance variation given the null is true. Some of them are very good, but I feel like the learning on this is going to be very low because I think a lot of people are going to click the buttons I clicked, which is all right. It's one of the reasons I do it, because I don't think this question is really that great. Sometimes I like my Pearson questions, sometimes I don't. There's other ones right here that are a little bit easier too. This one's basically the same stuff. Yeah, we're just getting warmed up today. We have to get one wrong to just get it out of our system. We'll do 2 more of these, then we'll switch over. But here, let's do a little practice. A high p-value is strong evidence that the null is false. So when do you have evidence the null is false? When the p-value is what? This one's super easy right here. We can just destroy this one. When do you have evidence the null is false? When the p-value is what? This one's so easily worded that we can just be like... This one I think is better so far. First part is just better. When do we have evidence the null is false? When do we have evidence the null is false? Who knows? When the p-value is what? We have evidence the null is false when what? So it's saying a high p-value, which would mean... Yep, exactly. Great job, Sloan, right there. If you had a high p-value, then you would have landed near the null. So your result would be near the null, and you would not reject the null, so you'd not have evidence the null is false. So a high p-value, let's see right here, same as false, because low p-value provides evidence that the null is false. Exactly. A very low p-value proves that the null is false. Do we prove the null is false? Do we talk about prove in statistics, yes or no? Do we talk about prove or cause? Like with regression, do we say this causes this? Or would you say I've proven this in statistics? Do we use the word prove, or do we talk about... No, we don't. We talk about evidence. Like we have good evidence. How strong is our evidence? How low is the p-value? The lower the p-value, the stronger the evidence. So right here, just the prove word is wrong. The statement is false because a very low p-value... No. Statement is false because very low p-value only shows strong evidence that the null is false. That's good right there. The statement is false because very... No. A high p-value shows that the null hypothesis is true. No. We don't show the null is true. So, hey, Jesse, good to see you here. We only what the null. We're not going to show the null is true. We only, sometimes you'll say retain it. We don't show the null is true, though. We either reject the null or we don't reject the null. So we don't show it's true. We just say we didn't have reason. We failed to reject it, right? So we don't have reason to reject the null. This statement is false because the high p-value shows that the data is consistent with the null hypothesis, but can never prove it. That's an S tier answer right there. It shows that what we saw, the data is consistent with the null. So what we saw was probable, i.e. high p-value, but we cannot prove the null is true. I just saw something that I would have expected given the null is true. A p-value of 0.05 is always considered sufficient evidence. Nope. Yeah, I know, right? Rare my Pearson W. I like that right there. A p-value of 0.05 is always enough evidence. No, just change your what. Is 0.05 always enough evidence? You can always just change your one. Let me get Jackson. Jackson had a question when they came into. Thank you, Jackson. But 0.05 is always enough evidence. Oh. This goes to your question, Jackson. Is 0.05 always enough evidence? And this literally goes to your question. And then I'll explain your question right here. Is 0.05 always sufficient evidence? Yes or no? It depends on the alpha level. And and so we're just talking about to reject the null. A good question, Millen, right there, because whether or not you reject the null does not mean it has practical significance. It only means statistical significance. So, Millen, right there, amazing questions and answers. And feel free to drop some questions. We could do some 322, talk about the end of the semester stuff we got planned. I'm going to probably do some fast baseball R with you guys, and might try to invite a special guest in. So the researcher picks the alpha. Right here, the statement is false because the null hypothesis is rejected when the p-value is below the value of alpha, right there, which may not be 0.05. Boom. Good stuff. We didn't get tricked by any of those. So the reason alpha is independent is because the researcher, Jackson, just says, I want to use an alpha of 0.01. That's how they pick alpha. So when we say it's independent, it just means anyone can pick any level of alpha they want. 0.01, 0.02, 0.05, 0.90. Don't pick wacky stuff. You can if you really want. Your research will just be tossed out the window. But when we say it's picked independently, it just means anyone can pick any value of alpha that they want. Does that make sense, Jackson? You're asking about, like, why is it independent? Well, the researcher just picks it. Tell me if you want more detail on it. Chapter 16, yeah. Let's look at that one here next. The frequency radio transmissions on birds. Oh, no. I mean, birds are not real, so that's problems in and of itself. Let's do one more of these, and we'll hop over to Jesse's question right here. Which of the following is true? A very low p-value provides evidence against the null. True or false? When you have a low p-value, what do you usually say? My p-value is low. I blank the blank. Ooh, good 2 questions. I like it. Is a low p-value, does it provide evidence against the null? Yes or no? What do you think? If the p-value is low, reject the null, and that means we have evidence against it, right? So we're saying when we reject the null, we have evidence the null is not true. We have sufficient evidence for the alternative. Now, we don't usually say we have evidence the null is not true, but by saying we have evidence for the alternative, we are saying I don't believe the null, so you have evidence for something else. So that sounds true to me right here. Very low p-value. Proof, just wrong right there. A very low p-value provides evidence against, no, we don't provide evidence against the alternative. A high p-value is strong evidence in favor of the null hypothesis. We don't think of it, if I understand the alpha, it doesn't matter. So you're blending, so there's a lot of ways these topics collide, Jackson. So you can look at increasing sample size in alpha and confidence levels. Is there a question specifically you're asking about? Because if you have a very low alpha level, you might require a larger sample size because they can work against each other. So an alpha level can be used for 1 minus alpha level of confidence interval. But the alpha level is 100%. The researcher says, this is what I want my type 1 error rate to be. That's usually the most consistent way people use alpha. So they say, this is my error rate for my research, a 1% error rate, a 5% error rate. Now, it does then kind of change. Maybe you might need a larger sample size when you think about things like power. So you're wondering about like power, because when it comes to power, if you were to have a lower alpha, then you would be decreasing the power of your test, and then you would need a larger sample size to maybe find results and have higher power. So that might be the counterbalance by which you're speaking of, because sample size, alpha, and effect size are all positively correlated with power. So if you were to decrease your alpha and you wanted to keep your power consistent, like let's say you're keeping the same power, but you change your alpha, then you would need to increase your sample size. Oh my gosh. No, which one are you working on, Sloan? Here, I'll finish this one off. We'll go right to Jesse's question. Then Sloan, tell me which one you're working on. A high p-value is strong evidence in favor of the null. A high p-value provides means that, yeah, data is consistent. That's what we mean. If a p-value of above 0.10 shows the null is true, no. No p-value ever shows that the null is true. Whether p-value shows the null is, no. See, the way we don't say the null is true. We just say that the data is consistent with the null. I feel like you could do more by, like, I don't know, they could have graphics and stuff on this and be like, point to where the result is on the graphic. I don't know. If the null hypothesis is true, you should get a p-value. You should get a p-value below 0.01. You can't. Oh, you can't? No. If the null hypothesis is true, you will get a p-value below once in 100 times. Yes. Good. Those are tricky. Tough questions. Let's do Jesse's questions here. Environmentalist concerned about the impact. So we just did 3 of those. Good stuff. Once again, it's just going over the definition of a p-value. So really good to know those, the definition of a p-value. The probability of our results or results more extreme happening by random chance variation given that the null is true. The only one that got me was the our results or results more extreme. I forgot to do the results more extreme and do that. The probability of a result here or more extreme than that, less than that, would occur about 1% of the time given the null is true. Little details, very, very particular details. Let's see. Where's the verbs? Environmentalists concerned. Here we are. Environmentalists concerned about the impact of high frequency radio transmissions on birds found that there was no evidence of high mortality rates among hatchlings nests near cell towers. They based their conclusion on an alpha of 0.05. So what do you instantly know right here? Yeah, exactly. Because it's saying like, what it's saying is, I'll go back to the graphic I drew on it. Is it saying the improper interpretation is this? So the 1% is saying like on that result, you'll get it 1% of the time. But then the correct answer on my Pearson was you will see a result at that or more extreme than it, like lower than it 1% of the time. Which I wish they used like context a little bit more. Like someone does this, like the 6-minute mile, I think it can make more sense. With the burbs. So we did not find evidence at the 0.05 alpha level. So what do you know right now? We did not find evidence at the 0.05 alpha level. What do you know? This is the key to solving this question. If we did not find evidence, no evidence at the 0.05 alpha level. So what do you know? No evidence at the 0.05 alpha level. Or we should say not sufficient evidence. Hey, Rachel, good to see you here. Is it, but wait, if we have evidence, so if we have evidence, then what? So if we have evidence, so they didn't find evidence at the, Great job, Jackson. Yep. Points in the chat. So for certain, because there was no evidence, the p-value has to be greater than or equal to alpha, right? When the p-value is high, we let the null fly. When the p-value is low, reject the null. So we know that the p-value has to be at least 0.05 or higher. So what would you do down here on the bottom at the alpha level right here? What would you do for that alpha level? We know the p-value has to be 0.05 or higher. So down here, you would definitely what? Reject or not reject the null. So down here, you would fail to reject. You would not reject at this alpha level. So there'd be not reject here because there's your p-value can't be in the rejection region. But up here, if we look at this 0.10 alpha, it's possible that the p-value is either here in the rejection region. That's where you would reject. Or it's up here in the fail to reject region. Now, the p-value could be anywhere. So the answer for what we do at the 0.10 level of alpha is that. Does that make sense? Because we know for certain at the 0.10 level that the p-value has to be higher than that bar down there. The p-value has to be 0.05 or higher, so it can't be below 0.01. The p-value being 0.05 or higher, exactly, there's not enough information to answer up there. So we don't know, maybe it's 0.06, 0.11. We do not know what the p-value is. So Jesse, does that make more sense on this one? They would... At the 0.10, they'd reach the same conclusion. We only know that the p-value is less than 0.05. No, not less than. They didn't have evidence. Really? Wow, it's such a wordy answer. Wow, it's such a wordy answer. Yep. There's the answer right there. They would reach the same conclusion only if it was this. Well, true. We don't know what the p-value is. We only know it's greater than 0.05. And so the key wording right there is they say less than, which is right there. Yeah. So once again, understand what is being written right here and understand how we're solving it, because knowing that the p-value is low and we reject the null is like one of the biggest things ever. So I think there might be a similar question here. A clean air standard. This might be the same kind of question. Let's see. These are pretty interesting. Like, I do like them. Like a long time ago, I figured out like drawing that graphic right there really helps understand the topic. Type 1, type 2 air. We've done a lot of the biggest stuff here. Why am I so tired? The clean air standard. Where is it? Aha. Oh, type 1, type 2 error. P-value less than alpha reject. Yep. And so here we are with a clean air standard. We are rocking and rolling through the questions today. Stat 201, chapter 16 quiz. A clean air standard. Okay. Let's take a look at the clean air standard right here. Many states require that cars be tested annually to make sure they meet these standards. I got to get my car inspected. It's on my board. Suppose state regulations double check a random sample of cars that they suspect repair shop has certified as okay. They will revoke the shop's license if they find significant evidence that the shop is certifying vehicles that do not meet the standards. Okay, so what is the null hypothesis for the shop? Just pause right here and write down the null hypothesis for the shop. So would the shop is doing a good job, like they get to keep their license, or the shop is doing a bad job, they need to have their license removed? What is the null? And they literally tell you what you're doing right here. So what is the null? And then we'll solve this whole question right here pretty much. So what is the null hypothesis for the shop? The null is your initial belief that you hold as true until you have evidence elsewise. So the null hypothesis is your initial starting belief that you hold as true until you have evidence elsewise. So what is the null hypothesis? Yeah. I'm so tired. I got like 7 hours of sleep last night. What is the null hypothesis right here? So this is the key to solving this problem. The key to this problem is what is the null hypothesis? And then we review what is type 1, type 2 error. What is the null? So they're looking for significant evidence that the shop is certifying vehicles wrongly. But Jackson, so here's the thing. They want to find evidence that the shop is certifying vehicles that do not meet standards. So if they're looking for evidence of that, what you look for evidence for is the what claim. So good job, Jackson, 100 points right there. If you're looking for evidence of something, that is the what-based claim. Whatever you're looking for evidence for is the what-based claim. So if you say we need evidence of this, then you're talking about the what. Well, kind of, but so when you say you're looking for evidence of something, that is the what-based claim. So if you say we're looking for evidence of this, that is the what-based claim, the null or the alternative. So if you're saying I need evidence for this, you're saying give me evidence for the null or give me evidence for the alternative. So which of those would you say you'd be looking for evidence for? The null or the alternative? Which of those is the evidence-based one that we need evidence to believe? Very important concept right here. Is the null what we need evidence for, or the alternative, what we need evidence for. Very important concept. So when they say, if they find significant evidence, I know they're saying that this is the what? Are they telling me right there that that is the null or that is the alternative? So it says, if they find significant evidence that the shop is certifying vehicles that do not meet standards, they'll remove their license. So is that the null or is that the alternative right there? Is this stating, because it says significant evidence, would that be the null or the alternative? We'll see if anyone gets this for 100 points. See, Millen, feel free to ask any questions you got if you want to know your about head out. But so they say they're looking for evidence for that. Evidence means that's all based on, I'll say the answer in a moment, but is that the null or the alternative? Very important concept. If they're looking for evidence, then that makes that the alternative based claim. So the null is the shop is doing a good job. And the alternative is that they're doing a bad job and revoke license. So they need evidence to revoke the license of the shop. They're not going to revoke the shop's license without evidence. They're not looking for evidence the shop gets to keep their license. They're looking for evidence the shop is doing a bad job and they revoke their license. Now, here's where we get to our big saying. What letter am I making right here? In a type 1 error, the null is what? In a type 1 error, the null is what? In a type 1 error, the null is what? Let's see who gets in the chat. In a type 1 error, the null is what? This is the 1, type 1 error. The null is true. Great job, Jackson, right there. And we reject it. That's the error. In a type 2 error, the null is false, and we fail to reject it. So let's look at how this applies right here. So in the type 1 error, what is true? Just explain to me what is true in a type 1 error. Good to see you here, Abigail. In a type 1 error, the null, explain to me what is true. Just tell me in a sentence rather than in a type 1 error, the null is true and we failed, and null is true and we rejected. So in a type, tell me about this type 1 error right here. So what is the type 1 error? Because we're doing this more like test relevant than solving my Pearson. Because we're always trying to learn for the test to be like, okay, in a type 1 error, the null is true and we reject it. So what does that mean for this question? So the type 1 error, the null is true and we reject it. What does that mean? So you have to look at the null and you have to say that is true. So what does that mean? Boom, Jackson. Exactly. The shop is doing a good job. It's true that the shop is doing a good job, but they are going to reject the null and say they have evidence the shop is doing a bad job because the null is true. They're doing a good job and they reject it. So let's see right here. And it says in the context, what is a type 1 error? They revoke the shop's license when it's only certifying vehicles that meet standards. Now you can kind of get type 2 pretty quickly by knowing that it's got to be the other way around. In a type 2 error, the null is false and we failed to reject it. So in the type 2 error, the null is false, but we are going to fail to reject it. So it's true that they're doing a bad job. The null is false. So if the null is false, the shop is not doing a good job. They are doing a bad job, but we are going to fail to reject the null and believe that they are doing a good job. So the regulators do not revoke the shop's license when it is certifying vehicles that do not meet standards. There we go. Which of these errors do you think is more serious? Well, this is a great question right here and really points to something which I should highlight more. Type 1, type 2 error is only context. Great job, Jackson, right there. So the context of a type 1, type 2 error really depends on who you are. The shop would probably love it if they made a type 2 error where they get to keep their license. People on the road are going to hate the type 2 error, though. The owner of the shop would consider a type 2 error more serious because the owner does not want to have their license revoked. I think so. Because no one won't. The shop owners, yeah. See, this is the owners of the shop would consider a type 1 error more serious because the owners would want to know if the shop's certification process is faulty. I mean, one could argue this. This is the problem right here. See how it says the shop owners would consider type 1 error more serious because let me review with type 1 error to just make sure what we marked. The regulars revoke. Oh, so type 1 error is going to be that. So type 1 error because more serious because you want to have it revoked. So the type 2 error is when they are a bad shop and they're doing faulty reviews, reviews of vehicles, inspections of vehicles that don't meet the standards. So I mean, one could mark this, but it literally goes to knowing the intent of the shop owner, and I think they're going to care more about their shop being open. But this means they're running a shop that certifies vehicles that aren't meeting standards. And then there's the environmentalists. So now they're going towards environmentalists with the type 2. So in a type 2 error right here, because they do not want faulty cars polluting the road, that'd be right there. Want to be like, they do not want, because they don't want, should be correct. There we go. I think in general, type 2, no, there's no in general. Good question, Jared Jackson. Really 100 points right there for asking. It's not that type 2 is more worse. Type 1, type 2, it's all context. It's which one is worse when it comes to type 2? 100% context. Because one's going to be a false positive, one's going to be a false negative. So which one is worse, to get a false positive when you think you have results when you don't, or a false negative to not find results when results do exist? That's what a false negative is, because you get like a negative result, like you don't find anything, but the truth is results exist. A false positive is when you think you have results, you reject the null, and you don't actually have evidence for the null. I mean, for the alternative. Oh my gosh, you shouldn't have rejected the null. So it's all context, Jackson, 100%, which this kind of gets to, like from the environmentalists, they're going to be more worried about this. Exactly. And from the shop owner, they're going to be more worried about this. It should say which one seems more likely. It should say the shop owner cares about money. Which of these do you think the shop owner cares about most? The environmentalists care about the environment, which is kind of inherent in their name. Which of these do you think they care about the most? So we usually, if we do this as written answers, which we used to do back in the day, we would take into account what people said. So it'd be like, which one of these errors do you think the shop owner, which one of these errors do you think the shop owner would be most concerned about? I think Jesse had a few more right here. A company surveyed. Wait, didn't we do that one? Oh no, we've done it before, but we'll do it again here. The primary shopper. We just did this one. This one's just like the one you did, Jackson. Aha. Oh my gosh. This one has a pretty good way of doing it. We've done this one before, but we'll do it again right now. Might take out my context here in a moment. Okay, a company surveyed. Okay, so what's the first thing we have to do with these sorts of questions? What is the first thing we should be doing with a question like this? If you see it on the test, we're learning for the test right now, and we're understanding what we would do if we got a question like this on the test. If we got a question like this on the test, what is the first thing we do? The first thing we're going to do is what? If you say it, I'll do it. Well, we can check the conditions. So we can do the hacks method or check conditions, but the first thing we usually do is
notation, brother.
Notation. We usually do notation first to make sure we have the right notation. That way we kind of know what problem we're working with, which will help us out. What of the notation on here do you currently know? Because we can get a lot of things on this. So what of the notation do you currently know? Because there's, I think, about 6 things we can get right here. We won't use them all, but there's a lot of notation. There's a lot of notation. I think there's 7 or 8 things. So they surveyed 2,300 men. They found 1,104 of them identify as the primary shopper. They believe 44% are the primary shoppers. They want to use a 98% confidence interval. So as long as you get part of this, you can get the next question, which asks about conditions. And I really think they do a good job with asking the condition question. So for this question, see what notation you can mark right here, because there's a lot. The notation we want to get to start is this is N. This is P, excuse me. I'm going to find that here in a second. This is X, and X over N equals P hat, which is the amount of successes over the number of trials. And so P hat is equal to, we'll clear this off right here. There's P hat, 48%. And then we can get Q hat, which is 1 minus P hat. We can get the Z star right here, which is going to be used for the confidence interval, which is 2.3263. And to show where we get that from, that comes from the apps right here. We need to go over to the apps and make a 98% confidence interval from the normal curve. Make sure you're on Z-scores, go between, and there's the number 2.3263. Round to 3 or 4 decimals. I usually do 4 sometimes, or 3. Next, we can go right here, and this is going to be P naught. If we were to use it in the problem, it's the hypothesized proportion, and this is Q naught right here. So there is, I think, all the notation. As I said, we have 1, 2, 3, 4, 5, 6, 7 things right there. 7 different things can be deduced from this problem automatically with the notation they give. So there we are, we're good to go. And that kind of leads into what they're asking right here on checking the conditions, because we always have to do random. So the condition is satisfied because there's nothing to indicate it wasn't random. Good. We need less than 10%. I wish they didn't jumble up the conditions right here. The 10% condition right here means we do less than 10% of all the men in the population. So this condition is satisfied because less than 10%, 2,300 men is less than 10% of the total population of men. And last but not least, we have the success failure condition, and the success failure condition states we need at least 10 successes, at least 10 failures. The amount of successes is 1,104. The amount of failures would simply be 2,300 minus 1,104, and that's the amount of failures, the amount of not men. And so we would say the success failure condition is met because there's at least 10 successes and at least 10 failures, noted by 1,196 not men and 1,104 men. And the reason we don't do nearly normal is because we're only doing the necessary conditions, and the necessary conditions are random, 10%, and success failure, because this is categorical data right here. Next, we have to construct the 98% confidence interval, and this basically goes to solving the equation. So marking the notation is a huge step that we always want to do at the start of every problem so we know what formulas we're using, because now we can go to the formula sheet and get the following equation right here. That is a Q hat, worst Q I've drawn in a while, and just plug in the numbers. So let's go right here and do P hat of 0.48 plus or minus Z of 2.3263 square root. And is this making sense, Jesse? What are your thoughts on this? Because now you know what we do. We're going to solve for the standard error, and then we're going to multiply that by the Z star to get the margin of error. Awesome. So now we're going to go right here, 0.48 times 0.52, and then divide by, oh my gosh. I don't know if I like the new calculator. Maybe it helps. People ask me to do it to help out with, and then 2.3263. There it is right there. And that is the margin of error, 0.035. There we go. And 3 decimals. Oh my. What does your confidence interval say about their hypothesis? So be careful. Do you believe 44% or not believe 44%, and why? Do you believe 44% or not believe 44%, and why? So just look at the confidence interval, and do you believe 44% or not believe 44%, and why? This is a big concept we use a lot right here. It's used in multiple questions throughout this chapter to understand why or why not we would believe 44%. And don't look at their answers. Just think about 44% and look at your confidence interval. So when you look at your confidence interval, and when you think about do you believe 44% or don't believe 44%, we don't believe it, right? Because 44% is not in the interval, we have evidence that more than 44%. Now, they get into something right here They want to see if it's greater than. Right here, let's double check. The significance level, and this is going to be interesting, is going to be, because they're testing greater than, right? Higher than. So because they're doing higher than, let me go to where I drew it out. Draw it out. Let's draw it out again. This is where usually people make the mistake because they throw a little trick in here. You ready? When we do a confidence interval, if we do a 98% confidence interval, then the two-tailed test will have what alpha level, Jesse? So what is the alpha level of the two-tailed test? 98% confidence interval has an alpha level on the two-tailed test of what? And the two-tailed test is the does not equals test. 0.02. And make sure we'll always put it as a decimal. Great job, Jesse, right there. 0.02. But here's the thing, Jackson, you might be on to the next part. He's doing a greater than test, right? So the greater than test has an alpha level of equal to half of that. The associated alpha level would be half of it because he's running just the one tail. Does that make sense, Jesse? Like when I've drawn it out right here, the 98% confidence roll is directly related to a does not equals test of 0.02 alpha. If we just do the greater than test, it'll be 0.01. And I think they even mentioned that in the answer. So we're hard on Mike Pearson, but they do explain it right here. The level of significance is 0.01. Since the grocery store owner is doing a one-tailed test, the level of significance is equal to the area. No, it's got to be this one right here. We have to have the area. Let me delete this in here. And as long as we haven't done anything crazy, oh my gosh, what am I doing today? Did I get the interval wrong again? I've been doing the math on these so wrong lately, and because I've been like not carrying a number. Oh, it's going to get mad at me for not putting these in. 98% confidence. It is the interval again. What am I doing wrong on my intervals? Let's look at my math, Jesse. I did it in my head to end. Let me check the math over here again. I'm going to go away from the scientific. Blame it on scientific calculator. Did I calculate p hat wrong? That's that. Does it want it as a percent? What? What have I done wrong? 2 seconds. What have we done wrong? P hat 1,000 points. Oh my gosh. 1,000 points. Do you see it, Jesse? The interval will be even tighter. Gosh. I'm going to pause here. Do you see the error? It's so easy to make errors when doing these. That's why I always like, and I wish we could just do. There we go. It's probably going to be about right there. So 46 to 50. Might even round to that perfectly. That doesn't round to that. So the error I used X instead of N. So I plugged in the wrong number. Yeah, Jesse, you got it. Yep. That's what it was. 1,000 points. Yeah, it's so easy to just plug in the wrong number and then wrong answer. So that's going to make the margin of error smaller because the sample size is in actuality bigger. So there it is right there. So it's 0.24. So the answer is going to be plus or minus that. So it's going to be not? Really? Oh, ha ha ha. Put the period right there. There we go. Because it's 40. This is the margin of error. 0.024 is the margin of error. So it's 48% plus the margin of error. There's the upper number. And then 0.48 minus the margin of error is the lower number. So if you put your numbers the right way, hopefully you didn't put X. Trenton, good to see you here. Make sure to mark your notation correctly. Catch me if I... Oh my God, that hurt. Shit. Jesus. Just slammed my elbow on a glass. My gosh. Ah! No. Ow. Yeesh. What should we do? Gonna just break things now, apparently. Ay, ay, ay. One of those mornings. Mondays, I know, right, Jackson? Oh, that did not feel good. I'm lucky I didn't break that glass. I came down like right on it, like right on that glass. So luckily, didn't break the glass. I kind of hit my elbow in like a tendon area. Make sure my tendon's okay. Oh yeah, what should we do? It is Monday. Got a little more time right now. What should we do? We've done a lot of the true false stuff. See what's going on over here. Chapter 16, a statistics professor has observed. Okay, let's go check it out. Here we are with a statistics professor. Yeah, Kelsey. Okay. Chapter 16. Okay, so with this right here, is this a one-tailed or two-tailed test? How do we know one-tailed or two-tailed? How do we know one-tailed or two-tailed tests? How would we know a one-tailed or two-tailed test? We would know a one-tailed or two-tailed test how? How do we know the one-tailed or two-tailed test? Because the one-tailed tests are the less than test, the greater than test. Well, we look at the sign, but how would we like... So when we do a one-tailed test or two-tailed test, we're asking about, is it less than, greater than, or not equal to? So the greater than test, the less and greater than are the one-tailed, exactly. And then the does not equals is the two-tailed. And then we look at the question. Great job, Jackson, right there. So the question will indicate, a statistics professor has observed that over the last several years, students scored an average of 70 on the semester exam. A salesman suggests that his software package can get students more involved. So automatically, this is sounding one-tailed or two-tailed to you. There it is. Predicts that it will increase. One-tailed or two-tailed? One-tailed or two-tailed? Spam filters. So it's one-tailed, yep. And so it's supposed to increase. So blank 1, 2, 3, 4, 5, or 6 we just found out now. 1, 2, 3, 4, 5, or 6 did we just find out the answer to? 1, 2, 3, 4, 5, or 6 did we just find the answer to? We just found the answer by saying, not quite blank 4. So when we do these, I'll write down right here in the general form. We have the null hypothesis. Yep, blank 5. Yep. Great job, Jackson, Jesse right there. The null hypothesis is some population parameter is equal to, and then we use one of these signs right here, some hypothesized value. So the null hypothesis is that some population parameter is equal to some hypothesized value, And then the alternative will use one of the signs right there. So we know that we're trying to say it's greater than the hypothesized value. What goes over here as the hypothesized value? No, hey, I'm getting questions wrong too, so don't worry. What goes over here for the hypothesized value? What is the hypothesized value currently? So take a look at what they're saying we currently have. So the null states equals, yeah, that's a good answer. The null has the equal sign. Boom, we know that. And what is the hypothesized value currently? Like, what do we currently believe is true? Well, not 100. Good answers, Kelsey, right there. We currently believe 70 is true. And so 70 is what we currently believe. And do we think it's going to be P or mu? So is it that the true proportion is equal to 70 or the true mean is equal to 70? So which of those is what we're talking about right here? Proportion equal to 70 or mean equal to 70? Because that's what we're testing, mu. And why is it mu? Because it's quantitative. So great job, Kelsey, right there. Excellent work, Kelsey. Another 100 points in the chat. Mu is for quantitative, so the true mean is equal to 70, and they're trying to show evidence the true mean will be greater than 70. So then what does a type 1 error mean right here? Well, we have to look at it. Someone say our famous statement here again. In a type 1 error, the what is what? In a type 1 error, the what is what? So we're talking about type 1. You have to think in a type 1 error, the what is what? So in a type 1 error, the what is what? So what does that mean, Jackson? This is true, but you're going to reject it. And you're going to say you have evidence of this. Because if you reject the null, you have evidence of the alternative. So what does that mean? The null is true. This is where people usually get stuck, because they'll memorize in a type 1 error the null is true and we reject it, but then you have to look at it and say, well, that means the null right here is true, but we're going to reject it and have evidence for the alternative. So what does that mean? So usually labeling it or writing it on it like this, the null is true, but what does this all mean and what are we going to decide to do? Because the answer is basically written out right now on what we're doing. Because we have evidence for the alternative, but the null is true. Well, not that they're less than. So the null is true. Students are still scoring around a 70, but we think there's evidence that they're scoring higher than a 70 with this new help thing. So what are we going to do because we think they're scoring higher than a 70? Are we going to buy the program or not buy the program? So are we going to buy the program that they're offering us or not buy the program that they're offering us? Because we think there's evidence they're scoring higher than a 70. So are we going to buy it or not buy it? We're going to buy it because we think there's evidence that it's helping. But in truth, there's no change. Their scores are still 70. Does that make sense? So we're going to make the error of buying the program when we shouldn't. So in a type 1 error right there, we mistakenly buy the program. So the professors think the scores, the professor buys the software and it doesn't help the students. So they kind of didn't go into a lot of detail right there, but it's not helping the students. The scores are still around a 70 and the professor buys the program thinking it helps. In context, what is a type 2 error? This is going to be simply the other way of doing it, where in a type 2 error, the null is false and we fail to reject it. So the type 2 error is going to be, we'll just do it 2 down. In a type 2 error, the null is false and we fail to reject it. So it's true that it's helping them. So the program is actually helping the students, but we don't find the evidence of that. Maybe we have like 3 students use it, a small sample size, and we make a type 2 error. So the null is false. It's false that the students have the same score, and we fail to reject it, so we don't find evidence for the alternative when we should have. So the professor thinks that the students score on average, they were scoring average. Nope. The professor thinks that the students score an average of 70 on the semester exam when they really score an average of more than 70 points. Well, this is odd, the way they're phrasing it. The professor doesn't buy the software when it helps students. Yeah. Explain what happens if the process makes a type 2 error. Yeah, I think that right there. A little worried about the answer right there. What is meant by the power of the test? So very clearly, you need to put this on a note card. The power is the ability to what? Power is the ability to what? And I'll basically show it on the screen. It's to something, what, the something, something. Don't worry, I know it. Power is the ability right there. Power is the ability to correctly reject the false null. It's not making a type 2 error. So basically, I like to interpret it as power is the ability to find results when results exist, because if the null is false, we should reject it. So when you think about power, it's the ability to correctly reject the false null, but it'd be the ability of the teacher to figure out that they should buy the software. Because if the test is powerful, they'll be able to figure out the software is helpful, which is rejecting the false null. So the power is the ability to correctly right there figure out that the software is helpful because rejecting the false null right there. We should have everything correct. Boom. No more answers wrong. Really good question. Type 1, type 2 error can be tricky. It's very exact on the wording. Power is the ability to correctly reject the false null. If the null is false, we should be able to find evidence that the software is helpful. And those are kind of the keys to this question. Does that make sense, Jesse, right here? Just working through this. Type 1, type 2 error is very tricky. Like, it's very easy to just reverse them. Nice job. And I think, did Kelsey have one? Random poll. Let's do the random poll one, and then Jesse has another one. A random poll. We've done a lot of these. There's that one. Spam filters. I think you wanted that one next, Jesse. And a random poll. We've done, like, the majority. We did bank lending another time. This one's very similar. We've done one like this, so we might try to speed run this one, but what do we do whenever we get to a question like this? What do we do whenever we get to a question like this? What do we need to do that I made a mistake on last time? That if you make errors here, everything blows up. Gonna have a bad time. Gotta mark our notation.
Notation, brother.
There we go. 100 points in the chat. Will you explain the relationship of power and the types of variant? Yeah, here, I can do it here coming up after this, Jackson. You got it. Yeah. Can't figure out notation? No worries. Let's do it. So here we are. Thank you so much, Kelsey, right there for asking. Really good question. Good practice. So here we go. So what notation do we have? I'll help out. Don't worry. Once again, I don't know. It's great answers. Whatever you get stuck on, let me know. Here we go. Is all the notation we have. What is the notation in this problem? So any of the notation you know, let me know, or any you don't know, let me know. And then we also need this right here. So what is the notation in this problem? So there's a lot of notation. A poll of 700 working men found that 9% of them have a second job to pay bills. We want to make a 95% confidence roll, and we are going to test the claim that 6% have a second job. So what is the notation? Now good. And so Jackson is a good review right here. So one thing to remember is that P hat has to always be between 0 and 1. So I think you might have found X right there, because you might have done 0.09 times 700, and that's actually P hat times N equals X. So you actually found X right there, and then you could try 63 over 700 equals P hat right there. So this is P hat. This is N. This is the Z score we need. This is what we are testing right there. And if P hat is 9%, then Q hat is 91%. Yep. And this is why I like to check right here and just practice. And then we do little checks with ourselves to be like, okay, P hat has to be between 0 and 1. So right here, and so you can back work it, because sometimes they give you different components to work with. X, which is the amount of successes, which would be how many working men had jobs, is 63 right there. Yeah, Jackson, great job and good practice. That's why I always just pause on the notation, because the rest of the problem is going to flow from this. Just remember moments ago, and I'm not impervious to this, because moments ago, Brian got notation wrong right here by putting X in, and the whole problem went wrong because I put X instead of N. Note right here how this is N, and so that's what you should put there, and I misput in X. So I used X where it shouldn't have gone, and my problem didn't work out. So it really boils down to notation.
Notation, brother.
We say that all the time right here. So mark your notation and then properly do it and catch any errors on my part. We'll show how that Z-score is found in 1 second. The Z-score, we would either give it to you on the test, or you'd use an applet picture. So we've got the apps right here. And the 95% confidence interval z-score is always going to be 1.96 right there. So you want to make sure you're on the z-score. Set it up the following way. 4 decimals is going to be 1.96 or 1.95996 if you go to the next decimal. So you don't need to go that far. So there's all the notation we need. Z-score of 1.96, very classic number in statistics. And now we go down here to the sample proportion is 9% plus or minus 1.96 square root. There we go. And I just don't lock the history. I like a smaller calculator. There we go. .12% is the margin of error. And so now we get, is it 1%? Now we get, there we go. Oh man, I did bruise my elbow. Ah! It wants as a decimal. So there's the margin of error. Three decimals. Hopefully we didn't enter something incorrectly. So what does the confidence interval say about the hypothesis? Is 6% in that interval, yes or no? Is 6% in that interval, yes or no? So do you notice 6% in that interval? What are your thoughts? Because you are 95% confident the true proportion of people who have a second job is contained in the interval. So you want to do your interpretation again. I am 95% confident that the true proportion of men who have a second job is contained in the interval 6.8% to 11.1%. I reject 6% because it is not in the interval. We do have evidence that more than 6% of men, boom, that's our redemption problem right there. Does that make sense, Kelsey? Thank you for asking this one. It's good practice, good review, and we've done a lot of problems today. A lot of easier ones to start. Not like in this, like over here when we do these, it's like it just asks basic questions. Well, we did some of those earlier too, but this one right here is going to be one. Ready? If the p-value is small in the level of significance, what should we do? Reject the null. When the p-value is low, reject the null. Just some fun problems. What is the probability that test correctly rejects the false null? That's the power of a test. Probability correct test correctly rejects the false null. What is the difference between the null and the truth? That's the effect size. Which of the following is the correct interpretation of a p-value that's not very small? What we saw was not surprising. What we've witnessed here, what we saw in the sample is not surprising. We fail to reject. We saw something that looks like what we would see according to the null. Is that all the easy, fun questions? What is the name of the threshold? That is your alpha level. There we go. Look at all those questions we just got done. So many questions. And then, are there other ones in here? Might not be. Spam filters. Let's do some spam filters. Also, which of the following can be made? What type of error is made when a true hypothesis is rejected? Type 1. Null is true. I'm seeing how much we can do today. What type of error is made when the false null is failed to rejected? Do I do which of the following true? I think we did. Well, let's check it out. Did we? Type 2. Yep. Null is false and failed to reject. And then spam filters right here. This is very similar to the previous one. Yes, Jesse, that one we just saw. Okay. So here we are with spam filters. And so whenever we're talking about type 1, type 2 errors, we probably want to know what the null hypothesis is. So when we look at it right here, it's asking, we can think of the spam filters as a hypothesis test. The null is that the email is real. So here we go with the null and the alternative. The null is real, and the alternative is spam. So what is a type 1 error right here? We haven't done critical value right now because I'm lost on if we have. I'll mention that here next, Jackson. Good question. So in a type 1 error, what are we talking about right here? So in a type 1 error, the null is true and we reject it. In a type 1 error, the null is true and we reject it. So what does that mean? So think about this is true and you reject it. So this is true and you reject it. What does that mean? Like what does this totally mean in a type 1 error? So you're saying it is true that it is a real email, like from a person you know, but you reject that. So what does that mean? What's the whole context of that? In a type 1 error, the null is true and we reject it. What does that mean? What does that mean? There is evidence it's spam. Is it spam? We find evidence it's spam, right? So is there evidence it's spam? There's evidence it's spam, but is it spam? Is the email spam or is it a real email? There's evidence that it's spam. Is it spam or a real email? Well, so is it a real email? So remember, in a type 1 error, the null is true. So what does that mean? You have to look at the null and say the null is true. So you just look at the null and you're like, that's true. So to go into detail, Jesse. Great job, Josh, right there. Jackson's right. So what does this mean we are doing in full context? You're basically there. So think about what you're saying. Everyone's just put together the pieces of what you have. In the type 1 error, we would this to a what email. In a type 1 error, we would this to a what email. You're right there. Like you've got the components of it. And so then we'll see their answer, which will say it. Mark a real email as spam. Exactly, Jackson. Perfect answer right there. It's a real email. It's true that it's real, like from someone we know, but we think it's spam. If they're like, hey, I found a way to get free money, we're like, that's spam. And they're like, dude, did you not see the free money thing? It was email I sent you. And you're like, yeah, it was spam. You're like, no, that was real. Which of the following allows spam to slip through your inbox? Very clearly, this is going to be a what now? Because we just said type 1 is when we mark a real email as spam. So type 2 is going to be when we do this. Type 2 error because the null is false and we fail to reject it. So think about this. It's false that it's a real email, and so we fail to reject that. So this allows spam to slip in because it's false that it's a real email, but you fail to reject that. This right here, what kind of email marks a real message as junk? Exactly what we said here for the type 1 error. It's true that it's a real email, but we mark it as junk. Type 1 error because the null is true and the filter rejects it. There it is right there. In a type 1 error, the null is true and we reject it. It's true that it's a real email, but we reject it as junk. This is, once again, I like to point out when my Pearson does well. This is when it does well. Some filters allow their users to adjust a cutoff. Suppose your filter has a default cutoff of 50 points, but you set it to 60. So this is saying it requires more evidence. Now, this is where it gets tricky. So this is, if you require more evidence, is more evidence saying you're using a lower alpha or higher alpha? If you need more evidence to reject the null, is that a lower alpha or a higher alpha? Alpha is the amount of evidence you require to reject the null, and it's a bar that you have to go under with the p-value. So if you say we're having a lower alpha, because they're saying they require, well, I just gave away the answer. Lower, great, Josh. If you're saying you're going to require more evidence, you're saying lower alpha. And so, interestingly enough, saying it has to have more points is saying it needs more what? Evidence. Lower alpha means require more evidence. A lower alpha because it requires more evidence to classify the email as spam. Should be right there. What impact does this change in the cutoff value on having the type of error? So this is an important time to review the concepts of error. And there are 3 things that impact type 1, type 2 error. So when you change your alpha, your sample size, or your effect size, you will increase any of these. Well, we're decreasing alpha. So if you decrease these, you will increase your type 2 error rate, and you will decrease your power, because power is 1 minus beta. So power right here is 1 minus beta, and power is positively related to all of these, but it's inversely related to beta because it's literally the complement of beta. Lower alpha because we have less. So they are inversely related. So all of these right here are inversely related to beta. So if you were to have a lower sample size, you'd make more type 2 errors. And that is the type 2 error rate right there. So type 2 error. And this is type 1 error. So if you have lower sample size, you have higher type 2 error rate. If you have a lower type 1 error rate, you have a higher type 2 error rate. If your effect size is smaller, which you don't control your effect size, it's just inherent to the data, then you would have a larger type 2 error rate, just what would happen when you do the math. So what would this do? What impact does this have on the cutoff value, on the chance of your types of errors? So this is literally lower alpha is going to decrease type 1. The risk of type 1 is decreasing, and then type 2 is inversely related. Yep. So literally lower alpha is literally, let's show that again. I'm just going to say literally every 5 seconds. Since you have made alpha lower, that is by definition type 1 error rate. Yep. So by decreasing alpha, you are literally decreasing type 1 error rate. That is what type 1 error rate is, or is your alpha level. And if you decrease alpha, you will thus increase your beta. These are thus inversely related, but it could have said, how does this impact the power of the test? The test is going to be less powerful. And less powerful means less ability to correctly reject the false null. That means more things are going to slip through that are spam. Now, you could just put the score to 0. Think about this. If you put the score to 0, you would stop all the spam, but then you'd have a lot of false positives because you would have increased your alpha. Does this make sense here, Jackson? Really good questions. I'll talk about critical values really briefly here. Critical values, I don't get into much. I don't find them to be of a lot of use, and I'll explain why. So when we do critical values, I'll show calculating critical values. Chapter 16, calculating critical values. So a critical value, critical values, the Z or T needed such that our p-value would be less than alpha. So it's an overlapping topic, because frankly, all you need when doing a test is to look at the what to see if you reject or don't reject. So all you need when doing a test is to look at the what to see if you reject or don't reject. It's the best way to do it. It's the way I do it all the time. It's like no software gives you critical values. Well, you look at alpha, that is correct. And then you look what to alpha. So you see that what is less than alpha. P-value, exactly. So all you do is you see p-value less than alpha and you're good. So, and good to see you here, Jacqueline. So what you can do, though, is you can calculate the critical value. So what a critical value will be is, let's say we are doing a does not equals alternative. And the does, so we're doing the null hypothesis states that the mean is equal to, let's say, 40. And the alternative states that the mean is not equal to 40. So when we run this test, we want to run it with an alpha level of 0.02. So that means our results would have to land in one of these regions. These are the rejection regions if our result lands over here. Because if our result lands over here, then what would happen? The p-value must be what? If your result were to land over there, then the p-value from this result has to be what? Because think it's further out than this line. They're not like confidence intervals, so to say. They'd be less than alpha. So the p-value, because this is the p-value right here, would be less than the alpha level. So the alpha level right here is the green amount. That's the alpha level, right? So any sort of result in these what are sometimes called critical regions are going to be less than alpha. But how could you get around this? All you really need to know right here is the p-value, because then you can just ask, is the p-value less than alpha? But what you can do also is you can go right here and say, well, I would reject, and the critical value would be, let's go here to the outside, and any z-score outside of this region would have to have a p-value less than alpha. Does that make sense? So we have a z-score here of 2.33 basically. So if my result comes back with something outside of this region right here, then the p-value would have to be less than 0.02, because this is the point where it's exactly 0.02 at a z-score. So the critical value, good for here, critical value is equal to a z of 2.33, and I guess we could put plus or minus because it's the positive negative. But once again, the reason I don't do this, I'm not a big fan of it, is because all you really should report to people is the p-value. When you use statistical software, it doesn't do a critical value. It just literally gives you a p-value. You go over here, you go to analyze. I think we're using this one. We might be using this one. Analyze distribution, effective average temp. You run the data, looks nearly normal, very nearly normal. You look at this, and also 77 is within the interval. So let's go here to test mean, and 77 is going to come back with a p-value of like 8% or something. We run it, p-value is 14%, and I knew it would be higher than 0.05 because it's in the interval. And all we do is just look at the test, the does not equals test, and p-value greater than 0.05. So that's, we don't go and calculate critical values. Like, I don't know anyone, I've never seen a business analytics or statistician person looking for critical values. They just go straight to a p-value because it's an intermediary step. And that t statistic right there is not the critical value. That is the standardized test result of the difference divided by the standard error found by 77, basically minus 76. It's just difference between those numbers divided by the standard error. It's going to be the negative version, though, because it's below. So there it is right there, and basically the negative right there. So I didn't round all the decimals, but yeah, and it's not going to be, and it keeps showing up is something that's not something super important. Jackson, thank you for asking that. 100 points, really good question on it. If you look at how we can kind of run test results right here really quickly, it's really fun how you can actually, like, let me show you the application of these chapters. We might end with that. Like the application of running tests, like how we run tests in business analytics. So that's why sometimes I get frustrated. Like, I don't mean to get frustrated. I'm just like, no one does it this way. Stat 201, application of tests and intervals. Okay, so I'm going to go a little quickly right here and check out the data analytics assignment where I also go over intervals. But if you want to create confidence intervals, they're super easy to create. So if you've got a data set right here, you could go right here to analyze distribution, and you could actually select only the categorical variables right here. So we're going to remove all the numeric. There's only 3 categorical variables. We're going to input all the variables here, click OK, and now I'm going to hold the control button and go to actually just stack. Let's stack right here. Now they're all stacked. Now watch this. You ready? Holding control does things to multiple graphics. So I'm going to go to confidence interval and 95%, and there's 95% confidence intervals for all these different things. I am 95% confident the true proportion of UT students who have a significant other is contained in the interval 51.9% to 59.2%, which is good evidence that more than 50% of UT students have a significant other. I am 95% confident the true proportion of UT students who are right-handed is contained in the interval 85.3% to 90.1%. As long as you know what you're looking at, you know what you're interpreting. So that's confidence intervals for the proportion and just how quickly we can do them. Confidence intervals for the mean, same sort of thing with analyzed distribution. We can just go over here to all the quantitative data by removing the characters. We don't have any expressions. Select all, look quick Y columns. We're going to stack the data once again. We probably shouldn't have done the identifiers. So can we remove this? We can. Identifiers are not something you usually analyze. So now I'm going to hold control again, go to the confidence intervals, and you can select any sort of interval, especially with other. So make sure to look at that for your assignment. Let's go 90% confidence intervals, and there's 90% confidence intervals for the mean and standard deviation of all the different data sets. And we just made tons of 90% confidence intervals. Now you might say, well, why am I doing this by hand? Well, you have to know how you're doing this and calculating this, because I can create one of these intervals pretty quickly knowing the formulas. So if you notice right here, the upper number right here for the mean, 27.66, well, that number right there is going to be the standard error of the mean, there it is, 0.83989 right there, 02 times about 1.97 because it's a t, which is a little bigger than the z. And then we simply add that to 26.278969. And that number right there, oh, I did 90%. I did that last time I said I could do it. So we got to redo it again. Why do I keep using different intervals? Most statisticians use 90% confidence intervals. 95%, my gosh. Times 1.66 about. And there's the margin of error. And then we add that to the 26.278969. And we get basically that number right there because I was doing it from what I thought the t was. And if you look at that number, it's very similar. So once again, I understand the components that go into this, the standard error and the t statistic. And then I realized my error in calculating it, that it was a 95%. I wish we could see the history on this because if you go back and check the video, that's the first number I should have got right there. I don't think we still have it in the calculator. Should have kept the history up. Can we see the history? I want to see the history. Oh, there it is. There it is. There it is, 27.93. And it basically rounds to it. So if you had rounded to the second digit, I would have done it by just using the summary statistics. I could have calculated that number right there. Well, there's 95 right there. I should have just checked it with that. So basically, we're able to do these things very quickly. Also, understanding the components that go into it, I can do it by hand if needed, and just usually do it pretty quickly. And I can go to the apps to get the exact numbers, but Jump's going to carry the decimals for me, or I could use my knowledge of how the T and the Z work. A lot of times what I do is I use statistical software like R to do the calculations for me, where I can do a proportions test like this, and it gives me the 95% confidence interval. I think it's conf level 90%. So there's a 90% interval now, and I can just change this to any interval I want. If I have quantitative data, I can do a t-test because it's quantitative, Mr. T, and I can go here to MT cars data. I can go right here and do miles per gallon. And there's a 95% confidence interval for the miles per gallon. And once again, I can take this other argument right here and do the confidence interval at 90% if I want. I can also test the proportion by going here to P, which is P, like the null hypothesis. The true proportion equals to some hypothesized value. And now I'm testing that the truth is that it's 80%. And I can also do it for here, but now it's called mu because it's the mean. And I can test something like 20, which I think is in the interval. So we obviously would not reject it. So the p-value is very high because it's towards the center of the interval. So, and there's the t, which is the standardized test result, and the degrees of freedom are 31, which lets you know the sample size is 32. I know I'm going a little bit quickly right here, but when I look at this output, I understand where it comes from. The degrees of freedom for the one sample t are n-1. The p-value is the probability of observing something like we saw in our data or something more extreme given the null is true. It's doing the two-tailed test. What is it? It's like sided, or let's go look at what it says for the notation on this. It is alternative. So we can go here to alternative, and we can just add in greater than. So now we can run the alternative the other way and get the other p-value. I also know if I do less, that the alternative now is going to be that p-value, and there it is right there. The reason is because the greater than, the less than test add up to 1, so I understand where these numbers are coming from and how they're being calculated. Question I had earlier, so if you decrease your alpha level, you decrease the risk of a type 1, and if you increase your alpha level, you increase... So here's the best way to remember, you ready, Jackson? If you increase your alpha, you do what to type 1? So if you increase your alpha, you do what to type 1? Because type 1 is alpha. So if you increase your alpha, you've done what to type 1? Increase alpha, you've done what to type 1? Increase alpha, done what to type 1? Because alpha is type 1. Increase. Great job, Rachel, right there. Excellent work. So it's direct. So this is type 1. This is alpha. So alpha is type 1. So whatever you say your alpha rate is, which is the amount of time you say you're going to reject the null, that literally is your type 1 error. So if you increase that, so these concepts right here, the reason I have them right next to each other, they are the same thing. Like your alpha is your type 1 error rate. Does that make sense, Jackson, right there? So alpha is type 1 error rate. So if you increase alpha, you increase type 1 error rate. So if you decrease alpha, yeah, we'll do one next. Might end with that one. So if you increase alpha, you increase type 1 error rate. So that is just inherent in what is done. But then type 2 is whatly correlated to alpha and type 1. Correct. Beta is your type 2 error rate. That's why I have these like next to each other right here. Those are the same thing. And if you increase alpha, you decrease beta. Now they're not one minus each other, But if you increase alpha, you decrease beta. So those are inversely related. So, and so is sample size to beta too. If you increase sample size, you decrease beta, which decreases type 2 error rate. If you have a larger effect size, which you don't manipulate effect size, you have a lower type 2 error rate. And then these are all, the first things there are positively correlated with power. So if you have a larger sample size, you have more power. So that's the way, and hopefully the arrow coloring right here helps you out. And power is 1 minus beta. So that is, these are 3 different things over here. That's thing number 1, thing number 2, and thing number 3. But the other things just have one thing on them. Does that make more sense right here? Understanding kind of what's going on right here, that there are 3 things that impact type 2 error. The three things are alpha, sample size, and effect size. If you increase any of those are inversely correlated with type 2, but they are positively correlated with power because power is 1 minus type 2 error. So if you decrease type 2 error, you increase power. So, and power is basically not making a type 2 error, which means not failing to reject the false null, which means finding results when results exist, i.e., correctly rejecting the false null. It sounds odd, but like a powerful test, it's like, imagine you're trying to see if Brian can run a mile in 6 minutes and you're trying to find evidence that I can't. So if the null is false and I can't do it, then a powerful test would be able to figure that out. So you could just say, I need you to do this every day for a week or every day for a month. The test that would be better able to figure out that I can't do it would be the test that had me do it for a month than a week because you've increased the sample size. Or you could have a higher standard and be like, well, if you're more than 5 seconds away instead of 10, and that would be increasing the alpha right there. You'd have a higher alpha level. So let me think. Yeah. Got it. Great job. So the more powerful a test, the less likely you are to commit a type 2 error. Yes, because powerful tests, or it's kind of the reverse of that, Jackson. It's the less likely your type 2 error, the more powerful a test, or a powerful test is less likely to commit a type 2 error, because type 2 error is what impacts power. Power is is created from type 2 error. Does that make sense? Yeah, I mean, what you're saying is basically right, but it would probably be better said like a powerful test is less likely to commit a type 2 error, or when there's a lower rate of type 2 error, the test is more powerful. So because power doesn't impact type 2 error, power is a derivative of type 2 error. Like it's a formula from type 2 error. But it's basically right there. Less likely to fail to reject the false null. Less likely to fail to reject a false null. Great answers, Jackson, and good review. These are big conceptual ideas right there that we're trying to do. And let's do, is it the scanners one? We might end with that. So we've done so many of these. Look at how much we did today. Wow, we did so much of it. Scanners for hidden weapons. So this is very similar. Let me mark this and we'll end with this question. I'll grab some lunch. Scanners for hidden weapons. A researcher. Okay. So with this question right here, with the researcher developing scanners for hidden weapons, he made his decision at an alpha of 0.025. Has concluded that a new scanner is significantly better. So does it sound like he found evidence or he failed to find evidence? Does it sound like he found evidence or he failed to find evidence? He concluded that they're better. Would that be something you need evidence for, or you would not need evidence for? He found evidence, right? So if he found evidence, what did he do to the null? If he found evidence, what did he do to the null? If he found evidence, what did he do to the null? He rejected the null, right? Great job. Awesome job, Josh and everyone. He rejected the null, right? So we know right now the p-value has to be what? So you're saying he found evidence here. So you know right now what? What do you know right now? What do you know right now for certain? He found evidence at the 0.025 level. So what does that mean? Yep. The p-value is less than this right here. Josh on fire right there. Great answer. We know the p-value is, yeah, and Jackson's got it right there. The p-value has to be less than that current level of alpha. So here's the thing. If we know that, would you reject the null right here? We know the p-value is in that region, right? So would you reject the null at the 0.20 level? We know the p-value is in the purple region somewhere because it has to be less than that. So would you reject at the 0.2? Yeah, you'd have to, because it's definitely lower than this. So this is reject. And we know to reject here. That's the one it told us about in the problem. But for this one, we don't know where the p-value is at, because this is reject, or not reject. Oh my gosh, not reject, and this is reject. It'd be reject. We're only talking about for this one right here. We're just talking about this idea. Because at the 0.0001 level, if it's above it, which it could theoretically be, we would not reject. But if it's below it, we would reject. So we don't know what to do there. Does that make sense, Jesse? This question can vary on how it's written. So you really want to draw it out and make sure you understand that if they find evidence, the p-value was below whatever alpha level they used. This question changes. I've had people say, but wait, I did exactly what you did. And I'm like, wait, but they changed the wording. So I really like this one. I think when you draw it out, it makes more sense, because you can say they found evidence at the 0.025 level, which means the p-value was below that. We do not know if their p-value is going to be below the 0.001 level, but we do know it'd be below the 0.20 level. And there are other versions of this. His decision would have been the same at the 0.20 level, but it may have been different at the 0.001 level. And this question does vary on how it's asked, so be very careful and draw it out. Then understand the concept of finding evidence means for the alternative, i.e. rejecting the null, p-value low. So a lot of good review, a lot of good p-value stuff in here. We've done the majority of these questions. What did we miss? Like 3 questions today? We only missed 2 or 3, did we? So person defaults on a loan. Which type of error did the bank made? So the bank needs evidence not to give them loan, right? Oh, wait. The more convinced the bank is that it's safe to make the loan. So we can think that, since the bank makes its profit from doing loans, will repay. If a person defaults, then the bank failed to reject the false null. So then the other one's that. Suppose the bank decides to lower the cutoff rate. So they require less evidence. So what is it? The cutoff rate is what again here? Any applicant with a lower point total than is denied the loan. So they're lowering the alpha level. What impact does this have? Well, then that's alpha level right there. So it's going to decrease type 1, increase type 2. Should be right. There we go. Good question. I know I just did that one quickly. Which of the following are mistakes that can be made in null hypothesis? Are mistakes. The null is true and we reject it. The null is false and we fail to reject it. 1 and 3. Free to the fall. Oh my gosh. We did these another day. Those are so long. Check out, I think, Thursday. We did all this. So 5 questions. And then is better to use an alpha level? Is better to use an alpha level? No, it just depends. Yeah, so it depends what you want. If we use an alpha level 0.01, then a p-value of 0.01 is statistically significant. That is true, because it's lower than alpha. If we use an alpha level, then we reject the null hypothesis. The p-value is... Wait. If we use an alpha level of 0.01, then we reject the null hypothesis. The p-value is... Yeah, that's true also. They're trying to trick me here. If the p-value is 0.01, we reject the null hypothesis for any... No. If the p-value is 0.01... Wait. Yeah, that's true also, right? My gosh, these are weirded so wordly. Wordly weirded. If the p-value is this, we reject the null for any alpha level greater than yes. Am I going crazy? Wow, that was interesting. They got me with all those truths right there. Which of the following are true? Using an alpha level 0.05, a p-value of 0.03 results in rejecting the null. Yeah, that's true. So the alpha level depends on the sample size. No, alpha level is set independently. You just pick your alpha level. Researcher picks it. With an alpha level of 0.01 and a p-value of 0.0 results in rejecting the null. No, it's got to be low p-value. Statement is false because p-value greater than alpha results in... No, statement is false. P-value greater than alpha indicates no. The statement is false. P-value only because only a p-value less than alpha results in rejecting the null. Using alpha level 0.05, a p-value of 0.06 means the null hypothesis is true. No. The statement is false because a p-value greater than alpha indicates no. The statement is false because a p-value greater than the alpha level only indicates that there's not enough evidence. That should be true. There we go. Yep. So really good stuff. Got one more. A p-value of 0.01 means null hypothesis is false. No, we got to see if it's less than alpha. Whether a p-value present depends on the alpha level. So just burning through these very quick. A p-value of 0.01 means null hypothesis has a 0.01 chance of being true. No. The p-value provides... Yeah. It's not the probability the null is true. A p-value of 0.01 is evidence against the null hypothesis. That's kind of... Well, whether a p-value provides evidence for the null... Evidence... No, not for the null. My gosh. So let me look at this one again. A p-value of 0.01 is evidence against the null. That's kind of true. This p-value proves no. Whether a p-value provides evidence for the null hypothesis depends. We don't provide evidence for the null. It should be evidence for the alternative. So I'm a little worried because whether a p-value provides evidence for the alternative depends on the alpha level. This p-value provides evidence for the null. We don't provide evidence for the null. So is evidence against the null hypothesis? Is it sufficient evidence? Well, that depends on the alpha level. So I'm a little worried on that one because the way they worded it. A p-value of 0.01 means we should definitely reject the null. No. False. Whether a p-value provides enough evidence to reject the null depends on the alpha level. So third one really? Was it this one I thought? Oh, it wasn't that one. We'll end with a wrong question. So it's the first one? Okay. A p-value of 0.01 means that the null hypothesis is false. So, no, it doesn't show it's true. This p-value provides evidence against the null, but does not show it's false. See, the problem is this is a correct statement, and that's what got me. Whether a p-value provides evidence against the null, because we have evidence the alternative is true, so it's evidence against the null. That is, so it's going to be this one right here. This p-value provides evidence against the null hypothesis, but does not show it's false. So they're really chiming in on this whole idea means that it's false. No, I'm not saying that it's false. I have evidence against the null. So that's what provides evidence against the null. But look at this. Whether the p-value provides evidence against the null, or you could say sufficient evidence. So maybe that's what they're getting into right there. But that's what caught me, is because p-value provides evidence against the null, but they're really chiming in on this false word right here, that we're not saying that we know the null is false. It doesn't show it's false. So they really wanted you to highlight that part of it. Yeesh. Really got me with that. So I think only 2 others. But yeah, so we did basically the full quiz right here. The other ones can be found, I think, on Thursday's office hours videos. Good work, everybody. My gosh, I need more coffee. Till then, bye for now, everyone. Bye.